welcome. I feel like I haven't seen you in a while. I haven't been up here in a while. Phil is not teaching today, obviously. I am taking over for the day, Wednesday as well. Wait, is today Wednesday? Yes, next Monday as well, I believe. I'll have to get the schedule straight in my brain. So, how's the assignment coming? Going all right? This one, there's definitely a lot of, I don't know why this is so echoey. Hold on. Maybe that'll help. I don't know why, or I don't know why. This assignment, where was I? This assignment is challenging in that there's a lot of moving parts to what you have to do, especially when it comes to downloading, not downloading the same file twice from different threads, and making sure that if you do download the same, or if you have two files that are the same, on the same server, that you combine them in such a way that it's all based on the idea that, well, A, we want you to be able to program challenging things, B, this is the way real life works, and C, the RSS feeds actually do have this issue where you could have the same article twice with slightly different information because you have ads in them and so forth. So that's why we're kind of making you do that. Anyway, there's more office hours. I have office hours tomorrow morning, and there should be office hours tomorrow as well with the CAs. Okay? Regrade requests for the midterm. If you haven't done those and you want to, please do those before next. I guess I made a deadline of Sunday, I think. So make sure you do that if you have regrade requests for the midterm. All right. We're going to start talking today. We're kind of done with the big part of threading, although today I'm going to talk about one more part of threading. I'm just going to show it to you. You are actually going to implement a thing called a thread pool for the next assignment, which basically is kind of like the farm assignment in that you've got all these, instead of processes waiting, you've got a bunch of threads that are all spun up and waiting for work, and they're just sitting there, and you basically launch another thread, a function to a thread that says, okay, now I'm ready to go, and it limits the amount of time it takes, or it negates the amount of time it takes to spin up all these threads. So you're going to be doing that for the next assignment. But today, we're going to start talking about networking. So networking is kind of the last big part of this course, actually, believe it or not, in terms of the kinds of things that we have to learn about. But we're going to talk today about building a server to actually serve information and building a client to actually ask for information from a server. And we'll see how that's done in C++. We're actually going to use a library that makes things a little bit easier than it might be. And then next time we're going to dig into some of the lower level details as well. Okay, so what is networking? Well, networking is just communicating between two computers on a network. All right, you can actually set up a network on a computer and then have the same computer talk to the server on itself. But basically the idea is you set up some server and you set up some client. They could be on the same computer. Normally they're not. They could be. They could be on different computers near each other, like the Myth cluster. They could be on computers on the other side of the world. Okay, and so you can communicate between them through some networking ideas. So on your computer, or when you have a network, you do need a server, and the server just sits there and waits. And the server waits until a client comes along and says, "Hey, do your thing and give me something back from your that you're requesting." Okay, how does this work on Linux? Well, it turns out that the server actually sets up what we call a socket, and a socket is a listener. Basically, it's a program running in the background that kind of says, hey, when some other computer accesses your IP address at a particular port, it basically says, hey, that request should go to your program. So your program, if you're a server, says, okay, operating system, I want to listen on a particular port on the computer. Okay, and it turns out that there are 65K available ports to listen on. It would be rare that a computer is listening on that many different ports, and in fact, some are set up for particular things. But you can think of a port number as kind of like a virtual process ID. So basically the host comes in and says, I've got my process, and you're going to, anytime someone asks for a particular port, go to my process with it. That's kind of how it works. So you can kind of think of it as virtualizing the actual process itself. Okay? You can see, if you use a command called netstat, excuse me, you can see what the ports are, like what's happening with some of the ports on your computer. Okay, so if we go to a myth machine, nope, not, yes I am in a myth machine, netstat, and then some PLNT, I believe it is. That's what you get. So let's take a look at some of these numbers here. What this says is what kind of port it is. TCP basically means your kind of regular IP address. In this case it means regular IP address and a particular way of sending information back and forth. And then it gives a local address. Notice almost in every case it's 127.0.0.1 something. That 127.0.0.1 means your local computer as you would refer to it. So all of your computers think their own IP address is 127.0.0.1 if they, or sorry, either .0.0.1 or .0.1.1. There's lots of different ways to refer to your own IP address. This is just the way it happens to be in your computer. I'm not exactly sure what the foreign address in this case is, but it basically tells you what it's doing. In this case, all those ports are listening, and there's a bunch of programs on there that listen for stuff to happen. The myth machines have them, your computer has them. Some of these are particular. Let's see, some of them, like for instance, 25 and 587. Those are the first two ports up there, and the port comes after the IP address. Those 25 and 587 are about email. So the myth machines and your own machine can actually receive email on those particular ports. 22 is SSH, that's the port that's listening. So the myth machines all are listening for SSH when you connect in. Happens to be listening on port 22. 631 is interesting. 631 is for your printer drivers. I'm not sure this is going to work on mine because I might not have set it up, but 170, what was it again? It was 127.0.0.1 631. 631 May, yes, there we go. I just went to this website on my local computer and it pulled up a little printer menu to like set up the printers and so forth. And if you go to that, you can do it. Sometimes you will also see your own IP listed as localhost, :631. Localhost is another way to refer to your own IP as you. So that's that. If you want to look up what some of these ports actually do, like the ones that I mentioned are the ones there, you can actually go to a couple lists. Let's see, here's a list from Wikipedia of all the port numbers. How do you get a port number assigned to a particular thing? Well, the low numbers, anything below, forget which number it is, anything below, where did it go? Say on here? I thought I put it on here. I think it's anything below like 1024 is going to be some group, worldwide internet group has to basically say, this is the port that's going to be defined for that. Like SSH, you kind of want it to be a regular port so that you don't have to always be typing 22, or it might be different on different computers. You also want the web, which happens to be port 80, to always be kind of the same one, or 8080. Those are the ones that are 80 anyway. It's going to be defined by this big internet organization. So if you look on this list I just had, here it is. If you look on the list, you can see some of these, like 22 is for SSH, 21 is for FTP, which is another way of transferring files. If I go down to 80 should be, there we go, HTTP, which is basically web services, okay? But anything above, actually does it say, it probably says on this web page here, there we go. Anything above 1023 are non-system ports, and you can pretty much use them for whatever you want, but you can also ask to have them not unofficially designated as your thing. So for instance, 1113 is the Licklider Transmission Protocol, which is used for deep space links. Kind of cool. So if you have a port 1113 open on your computer, hopefully you're listening for that sort of traffic. Maybe you're on a spacecraft. I don't know. But you can also go, the ones that don't get assigned are, or at least don't get assigned directly, are above, actually it probably says on here too, I think it's above something like 40,000 or something like that. Where is it here? Yeah, above 49,151 are not registered anymore, so you can just use those. In this class, we'll use like easy ones to remember, like 1, 2, 3, 4, 5. Are they in this range? Sure, but who cares? It doesn't really matter that much because nobody's probably listening on 1, 2, 3, 4, 5. Here's the interesting thing. If your computer is allowed to request a port, and that's basically the ones above 1023, if your program gets it, no other program running on that machine can get it. So if you do 1, 2, 3, 4, 5, then somebody else comes along and tries to do 1, 2, 3, 4, 5, they're going to get a message that says, sorry, that port's already taken. And that can be an issue sometimes. For our class, when you're doing networking, we'll all use the myth machines, but we will give you port numbers to use based on a hash of your username. So the likelihood of that crash, of that colliding isn't 0, but it's not too great either. Anjali. Can you assign a port to?
For example, can you change the web port to be like a
Oh, well, okay. So the question is, can you change the web port to be a different port? You can always set up a server on a port, and if you happen to be listening for web traffic, then then it will be a web address. It's not like if you go to 80, which is the web, the HTTP one, and you aren't listening for web stuff, it's going to break. Or if you are listening for web stuff on some other port, it's not going to work. It's all of this is kind of, there's a port. We're going to officially designate 80 as being the one that you normally go to request a website, and then the other ones are kind of up in the air. But yeah, nothing. There's nothing in the protocol about what you're doing with that port at all.
Does it mean that two servers do not have the same port number?
Two servers on the same computer can't have the same port number. Yes, that's correct. Yeah. So how do you do that? You just have a different port number if you want a different server. So you only have one web server on a particular computer, let's say. One general one that the world knows about, which would be at port 80. One sec. Lily, you have a question?
Yeah. How does the socket and the port number relate to each other? I know in the previous slide you said a socket.
The socket, so yeah, how does the socket and the port number relate to each other? A socket is the type of connection. Think of it like a file. So you open a socket, it's like you're opening a file. That socket happens to use the port number. That's how it works. So they're different ideas. A socket uses a port number to communicate to it. Think of it like a file descriptor if you want to. It's fine. You open a socket like you open a file. When you open a file, you get a file descriptor. When you open a socket, you use a particular port number as the number that you use to request things. Yeah. That was the same question. Okay, so anyway, you can go look at all these. There's lots of different ones here. Let's see, is there anything interesting in here? I don't know, you can find various. There's one called the I2P Bob Bridge in there. But anyway, you can request these, and somebody will probably give it to you if you have a good request. Yeah?
Oh, is the Minecraft port standardized?
Well, let's look. Minecraft. Yeah, there we go. 119.132. That's a different one, maybe. Minecraft, yeah. There's the 25565. There you go. All right. Anyway, yes, Minecraft is one that's on there. Okay, so that's the basic idea for ports. We will use ports when we open them up. We'll have to choose the port that we're going to listen on. Okay, and like I said, for your assignments, we'll have the script will actually determine it based on your own username, or your program will. But otherwise, we're just going to use like 1, 2, 3, 4, 5, and so forth. Okay. So if you want to be sneaky during class, you can go open a port up that I'm going to use in class, and then I won't be able to, and I'll go, what's going on? And then you and your friends will laugh. Yeah.
Why is it that PID/program name is not?
Oh yeah, good question. Why is the PID/program name not filled in? It turns out that you only get that filled in when you either own the process or are able to see other processes like your root. So it hides that from you. Just because it's like you don't get that information. It'll tell you which ports are open. It just won't tell you which process you can go to. When we run one, we'll check this again and see that our program should be on there because we're going to be able to check it. Okay, so that's the basics of networking. Let's create our first server. Okay, there, like I said, there's some library support here that we can do, but let's do a time server. I'm going to do a particular one called time server descriptors. Okay, and here's what we have to do for it. Okay, we have to create that socket. Okay, so we can do something like this: int server equals create server socket 1, 2, 3, 4, 5. That's going to be the port number that I'm going to ask for. Create server socket is a library function that we will go into a little more detail later. But for now, just know that it opens up a socket to listen on that port. Okay, so that's all it's going to do. Okay, and then what we're going to do here is we're going to serve the time. So we're going to basically use, we are going to get the time off of our system and wait for a client to try to actually connect to our port, and then we're basically just going to shoot the time back to them. Okay, there are time servers out there that do this. If you turn on your computer and it has no idea what the time is, it will probably go ping some time server, get the time, and update the time automatically for you. Did anybody have to change their iPhone's daylight savings time last week? No, it did it on its own, right? Yeah. When it does it on its own, it generally either knows when daylight savings time is, or it just keeps track of the server and asks the server what time it is every so often. And after daylight savings time changes, it goes, oops, now I got a different time, and it sets it. So this is basically what we're going to do here. We're going to basically set this up. A server just sits here and waits while true, okay, in some loop. Okay, and it's not, the only way to stop this one is going to be like killing the process. Okay, Control C works just fine. A SIGINT. And what we're going to do is we are going to wait using this command called accept. So we're basically going to say int client equals accept server, and then in this case we're not going to pass any other parameters on here. If we wanted to use those accept parameters, that could get us information like, hey, what's the IP address of the computer that's requesting it? Because we may care about that. Okay, but in this case, I'm not gonna care what that is. Okay, and then once this will block, accept sits here and just blocks until someone comes in and does the request. And then once we get the request, we'll call this function called publish time, which we will write right now. Okay, so that's the whole server, except for the publish time part. Yeah. Is publish time? Oh, accept is another, yeah, accept actually, I think accept may be just a system call. Man to accept, I believe, yeah it is. It's a system call that's to accept a connection on a socket. Okay, and let's see, does it say anything? Yeah, it's got flags and addresses and so forth in there. Okay, all right, so let's write this publish time function. Static void publish time, pass in a client, which is gives us the actual, that gives us the, not the socket in this case, but it gives us the information about the client to be able to send it back. Basically has the information about, hey, where do I send this response? That's what this is going to do. And it's got another kind of like a file descriptor as well. Same sort of idea in this case. Okay, all right, so what do we have to do here? In fact, it is not only like a file descriptor, it is a file descriptor, because in Linux, pretty much everything's a file descriptor. Okay, so what we're doing here is we're going to get the time. Now we have to call a couple other functions. I'll talk about these in a second. We have a type called time underscore t. I'll just call that raw time. And then we use a time system call to actually populate raw time with an integer. As it turns out, it's just an integer. Then we have to get the details of that time out. So there's another one called struct tm, and I will just call it ptm equals get gm time raw time. What this does is it takes that raw integer, which is the number of, I think it's the number of seconds since 1971, basically. I think that's what it is. It may actually have milliseconds in there as well. But so I guess maybe it's a yeah, I think it does. I think it does a millisecond. But anyway, what this gm time function does is it takes it and converts it into a form so that we can read off the details. In fact, we can call another function to do this. Let's do the following. We need to convert that number into something that's human readable. So we're going to create a little array, time stir. 128 is actually big enough. This is when people write things like that in their code, that means it's ripe for hacking, for what it's worth. But that's the way it goes. And then we're going to call strf time stir to actually say, pass this in. And I'll show you this function in a minute. Size of time stir. Oh, good. At least somebody's going to keep track of that. And then %c, which is not the same %c as printf, ptm, like that. Okay? So that does that. Let's look at that function for a second. Man, strf time, I may have just spelled it wrong, but anyway, what is this? It says format the date and time, and it takes in some buffer to populate, it takes in the maximum bytes, it takes in the format, and then it takes in this struct that we get from the timer. Let's look at what that struct is. All the different formatters are in here. Let's look at what %lowercase c says. It says print out the preferred, or create the preferred date and time represented for the current locale. In other words, Linux knows like where you are located based on when you installed your operating system, and it says, oh, some people have determined, hey, this is the format that's normal for that location, or the preferred date and time representation. That's what that does. There's lots of different ones in here to do. Okay, all right. Okay, so that's how we're going to do that. Now, because this is a file descriptor, how are we going to write the information from that file descriptor, the socket? How are we going to write to it? Well, yeah, we're going to use write, which means we have to go through this stuff here, like size underscore t num bytes written equals 0 size underscore t num bytes to write equals the length of this string we're about to send out, strlen of time string. Okay, and then what are we going to do? We're going to do like while num bytes, num, wish I could type today, bytes to write, while num bytes written, because we could have done it, is less than num bytes to write. We're going to actually go and do this while loop where we're going to do the following: num bytes written, let's see, plus equals write client, and then time stir plus the num bytes written, and then we're going to do num bytes to write minus the num bytes written. Okay, all right, and so that does the output. Now, turns out that it's actually really important to do this in a while loop now, because now we're dealing with networking. Networking very frequently will not send all the bytes we ask it to. It'll try, but then maybe something else, hey, it can only send a certain amount at a time and whatever. So write many times will not send all the bytes. So doing it in a loop here is particularly important in this case. After we get done, we can just close the file descriptor because we don't need it anymore. And that should be it. Okay? There's our client, or our server. Okay? Basically sets up a socket, waits for some other computer to say, knock, knock, please give me the time, and then it publishes the time to that client. Okay? Yeah.
What happens if the client disconnects before?
Yeah, good question. If the client disconnects before, it normally doesn't matter. You're shooting off to this file descriptor, and if the file descriptor is closed, yeah, your write might get an error, I suppose, but in this case, it's not going to matter. Yeah, or we should do more error checking, but yeah. Yep.
In this case, I see that you declared client in line 40, and then it's like within the while loop scope, and then on the other side, like on the other function, you call client. So is client here kind of like a global variable of some sort when you?
No, it's just passed into the function.
Oh, it's passed. Okay.
Yeah.
But you forgot to pass it.
Yeah.
Oh, I did? Oh, thank you very much. Maybe that's the problem. Publish time. Yes, good point. Is that better? Yeah, okay. Let's see. Did anybody see any other mistakes? Make time server descriptors. Okay, so now what time server descriptors is going to do is nothing right now, right? It's going to try to open up port 1, 2, 3, 4, 5. Luckily, none of you know enough about this yet to do that yourself. So it opened up 1, 2, 3, 4, 5, and it's just waiting. Okay, so we can go to another computer. This one I happen to have on, let's see, this one's on Myth 66. This one I logged on to Myth 53. I happen to have already created the client. We'll write the client ourselves in a minute. Time client. And what you need to do for time client in this case is tell it which myth to go to. In this case, it's Myth 66, and then 1, 2, 3, 4, 5 is the port. And if we do that, look what came back. The time. Right? Amazing, right? But that's exactly what happened. And let's prove to you that something's going on here. First of all, if I close this program over here, if I try to run the time server there, it says assertion client socket greater than 0 failed. So basically, we didn't get the connection. Okay, and we could also do let's do this. There it is. Let's see. Instead of writing the time, let's just do this. Time stir 0 equals H. Time stir 1 equals 0. I'll send an H. See if that works. Make time server descriptors. There we go. And if we go over here now, we have to run it. Time server descriptors. We have to run it. And then over here, now we should just got an H. We didn't even get a new line. We just got an H, right? And so, and then the rest of it because, I didn't put the 0 didn't work in there. Not sure why. Anyway, point is that it's really doing what we asked it to do, which is connect to the server. Okay. In fact, let me change this back. Time server descriptors. Time server descriptors. Okay. Make time server descriptors. Okay. So if you wanted to, once I start this off, any of you could also go to that thing just from your terminal, and you could if you had the client. I'll show you how to do that in a little bit as well. How to do that. Actually, I can show you right now. There is let's see. This should work. Let's see. If we do telnet, that's another connection one. Let's see if this works. Myth 66. What port is it? 1, 2, 3, 4, 5. There we go. You can telnet. So you can do this on your computer. You can type telnet and then Myth 66 1, 2, 3, 4, 5, and you should hopefully get the current time, which is there. Okay. The bigger question is, why is that time wrong? Let's see, 1959 is probably like GMT or something like that. Yeah, time in Greenwich, England. Anyway, questions on the server? What we're doing so far? Good? No questions at this point? Yeah.
Are all the requests handled sequentially?
Yeah, it's such a good question. All the requests are handled sequentially. So if I put a big sleep in there after the accept, and all of you started getting the time, you would all be delayed until the network got along, until the program got around to doing that. Like there's no multi-threading here or whatever. We'll get to that in a little bit. Okay. Yeah.
What I'm just so confused about is like who can connect to it? Is everyone on the same Wi-Fi network? Everyone on the same actual computer?
Yeah. In this case, I was running it on a Myth machine. Those Myth machines are available worldwide, although I bet that port is blocked. So you can, because of security reasons, you can set up your server, your computer, to block requests on ports that you don't want to accept them on. So the things that you can go to the Myth machines from outside the world are basically port 22 for SSH. So probably computers from the outside world could try to connect to this, but then it would get denied because the operating system says, I don't want outside people from our network connecting to any ports. We happen to have them open for internal to Stanford network. Yeah. Other questions on that? Good question. Okay, so so we kind of went over the details of this. As I said, the while loop in there for the writing of the bits was kind of important, but it gets annoying really fast to have to write those while loops. So what we're going to do is we are actually going to use a library that allows us to use C++ I/O streams with the less than less than operator to actually do this a little bit easier, right? So in this case, it's going to look like this. Okay, in this case, it's going to look like this. Instead of doing it, I'll just show it to you right now. What we're going to do in this case is we are going to create a socket buff. Okay, this is using this library that we give you. Create a socket buff, which basically takes in the client's it takes in the client's file descriptor and then creates a little what's called a sock buffer, which does the buffering for you. You know, it does that while loop and uses write and all that. And then we create a socket stream, which is very much like cout, which allows you pass in the sock buffer into that, and then you can do SS less than time string, etc. So you're not going to have to do all this write business with while loops and all that. You're going to always convert it into a little sock stream like that and go with it. Okay, so that's going to be kind of nice. That we're not going to have to worry about doing that anymore. Okay, that'll be nice. Okay. So the question already came up, hey, this happens sequentially. Maybe that's not the best idea if you've got to send a lot of data and you've got to, or you have lots and lots of people trying to communicate. It probably wouldn't surprise you that if you go to google.com or you go to web.stanford.edu, there's not one server program that's just blocking every time someone comes in with a request. Right? Google would never have become a company if they had done it that way, right? They have to actually have your web server able to handle many, many requests. That's not to say that it will always be able to handle all the requests. There's a thing called a DDoS, which is, what's the first D stand for? Distributed, yeah, distributed denial of service, which basically means lots of people try to connect to your server and it overwhelms it. It's really hard to actually stop that from happening if you can get enough people and enough computers to try to connect to your network. But one of the ways we can make it so that this doesn't block is the following. In fact, I'm going to show you how we're going to do this with a slightly different program called Time Server Concurrent. .cc, okay? And we're going to do the same exact thing as before. We're going to write these two functions, and they're going to be somewhat similar, except that now, notice what I've got up here. I have included another thing called a thread pool, and like I said, you're going to write thread pools for your next assignment. But I want to show you how they're actually used, because they're pretty straightforward, as it turns out, to actually use them. So same thing as before. We're going to do a server, and we're going to do create server socket, and we are going to do that on, let's say, 1, 2, 3, 4, 5, and we are going to do a thread pool, which basically says create, in this case, 4 threads for me, get them going, and then later I will be able to send a function to one of those threads to be able to run, and then I can go back and accept another client. So I'm going to accept something, and then I'm going to do that. In fact, I'll do that right now. While true. Okay, what are we going to do? We're going to do int client equals accept server null, because we don't care about the IP address, etc. right now. Okay, and instead of just calling the accept command directly, we're going to do the following. Pool.schedule. Okay, what's this going to remind you of? Client, I'm capturing that, publish, time. Oh, sorry, the accept will, we do block on the accept. After the accept, we actually just make the publish time function go onto the thread, like that. Okay, so we're basically saying to our thread pool, run the publish time in a thread, and let me get back to accepting clients. That's what's happening here. And that's actually the extent of it. That's all we've changed in there. But now we've got 4 threads that are all going to be running concurrently and all doing this publish time. Okay? The one thing that we have to do, which is interesting, is when we write the publish time function, it's going to be similar to before. We're going to write time t raw time and then time ampersand raw time. That's not going to change. Okay? But it turns out struct tm, we'll call it tm in this case. It turns out that that function we used before called gmTime is not thread safe. Doesn't actually work that way. But luckily, many of the functions that are built for Linux have been written as thread safe functions. You just have to call them slightly differently. So in this case, we're going to do, before we called gmTime, now we're going to do one called gmTime_r. The _r is for reentrant, and most Linux system calls or functions that are reentrant, in other words, thread safe, have the little _r in there. Okay, so you're going to do that, and then we're going to say, at raw time, and now we're going to publish that to our struct that we have there. Okay, why wouldn't that work before? Well, it turns out it reuses some of that internally when you do the regular gmTime. It's just not thread safe. When they wrote that function originally, they didn't care about that. So that's the way it goes. Char time stir, 128 in this case, big enough for most non-hackers. Okay, and then let's see, we're going to do same things before, strf time stir, and size of timer, time stir, and then same thing, %c, comma, tm, like that. Now we'll use the sock buffer, sock buff sb client, and then we will do an IO sock stream, ss and sb, like that, and then we're going to say ss and time stir and L, and that's it. The nice thing that I didn't mention before about creating this sock buffer, when it goes out of scope, it closes the client for you. So you don't have to do any more close in this case. It's kind of a nice thing there. Okay. All right. Questions on that? Let's see if it works. Anybody see any? Time server concurrent. Looks good. Time server concurrent. If we run it, should be running on 1, 2, 3, 4, 5 again. And if we go and request 1, 2, 3, 4, 5, we get the correct time. So there you go. Okay. Question, Liam.
And one reason why this is especially important is because most publish functions would have to publish, say, a 10 megabyte website instead of just a 128 character string.
Right. So the question is, wait, why do we care about these thread pools? Part of it is that you may have to deliver a lot of data in your publish time or whatever function you're doing the reply to request. So part of that is that, and then in the meantime, if other requests come in, they just bunch up. The other one is that you want to be able to accept a request pretty quickly. There is a timeout in there of some sort, and it does mean that there are some. If I try to go to a website, sometimes it'll time out if it can't handle it in the amount of time. So you want to limit the amount of time that happens. Yeah.
Are you able to make the accepting multi-threaded?
Yeah, good question. Could we have made accept multi-threaded? I doubt accept is actually thread safe, believe it or not. It might be. I'm not 100% sure. But in this case, it doesn't really matter. The problem with that is, here's why you wouldn't want to do that. It's a blocking function anyway, right? So you want to block anyway. I mean, I suppose you could say, hey, I'm going to call those 4 threads with accept, but then you'd also have to have some other blocking mechanism in there to wait for the threads to be done and do another. I mean, it probably wouldn't be the best idea.
When a web server, though, like Google or something is receiving a bunch of requests, does that mean that they're just like going through accepts? Is that like super?
Yeah, if when Google or whatever is getting a bunch of requests, they've got this loop that's just spinning really fast, and they have millions of threads here that they're throwing those off onto, or thousands of threads.
But it just processes like Google.com processes one accept at a time.
Well, this particular, so it's a little more subtle than that. There's not just one server that everybody in the world goes to, right? You go to google.com and there's a distribution. You know how you type ssh.myth.stanford.edu and you get one of the 12 myths available? Well, which one gets available? There's a little program that basically decides, hey, which myth is least busy right now? You get to go to that one. And that's how Google works too. When you try to connect to google.com, it will start by going to a particular computer or two or however many, and then immediately farm you off to various other ones. So yeah, that's how giant websites scale like that. Yeah. Yes.
Is this like the standard C++ way to do it, or is like the create server socket or the functions like the same? I'm just wondering, like.
Create server socket. I believe that create server socket. Because the question is was that a Stanford way to do it or not? I don't think. Hang on, man. I don't think create. I'm almost certain. Well, it's not a. It would be a C++. It's not a C function anyway. I think. Let me think about this. I believe it's in socket.h. I think it's in there. Yeah, I think so. I'll have to look that up for you. Yeah. Okay. So that's how to create our server. We haven't created the client yet. We'll do that in a second. Okay. So this is how we can do it with the thread pool. Okay. I talked about why this. Hey, let's talk about time for 1 second. For one more second. Oh, no pun intended. Really wasn't actually. If we are getting a time and it's an integer, right? It used to be on most Linux systems that the time was a 32-bit integer, right? And it's the number of seconds since 1971. Why 1971? Well, they were building Unix in the 1970s, and that did it. And that's why they picked 1971 as like the beginning of time. And they chose that, and every second this integer counts up. What's going to happen when we get through all those 32 bits? It's gonna end up. Who's heard of the Y2K problem from before most of you guys were even like conscious? That was an issue back in the early 21st century. Like actually, 1997 was about the first time most people had heard about it. They had an issue where the time in many programs was the year in many programs was actually stored as a 2-digit number. Like 1999 would have been 99. So the minute you went over the year 2000, it would go back to 0. And people literally thought that the world was going to collapse because computers around the world were all going to like die at that moment, or ATMs were going to start spitting out random money into the street and whatever. But people thought about it early enough. One of the most interesting parts about that is that even today, and this is a crazy fact, there is a lot of software running on big computers, mainframes and other kind of computers, written in the COBOL language. COBOL was invented by Grace Hopper. You should look her up if you don't know who she is. By Grace Hopper and others in the 1950s. It's one of the oldest programming languages. There's still a lot of banking software that's written in COBOL. In like 1997, people were going, oh my gosh, we have to fix all these problems with these computers because the year 2000 problem. And they had to go hire all these COBOL programmers who had been retired for years. And so they ended up hiring all these COBOL programmers. And I've heard COBOL programmers were like, wow, that was like winning the lottery because you could charge whatever you wanted. Nobody else knew how to fix these problems. And you were just doing it in retirement because what else are you doing and whatever. And bought that new vacation house or whatever. But anyway, we're going to have the same sort of issue relatively soon. Should we do the calculation for that? So 32 bits, okay, that's 2 to the 32, meaning we have 4 billion, actually I think it's actually signed, so it's actually divided by 2, so it's 2 billion seconds. How many years is 2 billion seconds?
62.
I don't know, let's figure it out. This number, let's see. We have to take this number and do what? That is the number of seconds. So divided by 60 gives you the minutes. Divided by 60 again gives you the hours. Divided by 24 gives you the days. Divided by 365.25 gives you the years. 68 years. Yeah, 68. So 68, 1971 plus 68 is 2039. So in 2039, which is coming up, not tomorrow, but it's coming up, there are still going to be computers who are going to have a similar sort of issue where the time actually wraps around and we end up with this issue. So that's that. Most Linux systems now have been retro kind of fitted to use 64-bit time, which would mean like the end of the heat death of the universe before they roll over. So we're actually okay there. But the problem is that there are still a lot of programs that would need to be recompiled using the new thing. So kind of issues with that. Yeah. Why is time signed? Because they used an int originally or whatever. They used a long or whatever. I mean, it was just, they didn't necessarily think that far ahead for some of these things. Just, it's the way it goes. Okay, so let's actually, I got the published time. Let's actually implement the client. So what we'll do is we'll do time client. Let's see, I think I've got the starter code in here to time client.cc. Oops. Yes, and time client.cc. Okay, so in here, we're going to, what did we say the client needs to do? The client basically needs to request from a particular port a connection and then just get the information back from it. Okay, so in here, we are going to do what? We are going to, I don't know why it says code there because, oh, there we go, yeah, code. Okay, we're just setting it up so there's a bit of error checking in there. Okay, and what we're going to do here is we're going to set up a client socket instead of a server socket. Client socket equals create client socket, and we are going to, in this case, argv1, and then we'll just do our ATOI, which is ASCII to integer, argv2, which is going to set up the server. So the client socket has to say, hey, who am I connecting to and on what port? That's what that's going to do. Okay, and then we're basically going to check and see that the client is greater than or equal to 0, because it means if it's -1, it will say, oh, we didn't actually get a connection, so we'll actually stop in this case. Okay, in this case, all we're going to do now is we're going to say, okay, let's create a sock buff, sb client socket, okay, and we're going to do io sock stream, and we're going to pass in our SB. Oops, I think it's like this, SS, SB, like that. Okay, and then we are going to, since this is C++, we can do string timeline, let's say, and then getLine works. GetLine from our stream into timeline, and cout timeline end L. And is the return 0, and there it is. That's our client. Okay. So far, so good. That's all we really need to do. We need to open the client socket. We need to create a little socket buffer and a stream to get the data back from the client, and then get the data, and then print it out. Done. Yep.
Which point here is it actually waiting for the server to set?
Yeah. So there's right here when it's creating the client socket. That's when it's waiting for this client to set up the socket, or for the client to set up the connection. Basically, this is the part where it goes out to to find the IP address, tries to connect to it, and so forth. And when it gets a connection back, it will then move on.
But where does it get the time data?
It gets the time data down here when it says getLine. Remember, this is we've created a file descriptor as the client socket. Once you have that, you can read from it like you would normally read from any other file descriptor. Okay. Yeah. Wouldn't the client have to wait until the server finishes writing data? No, not necessarily. It knows that it can get a whole line first. Like it can read the line, and the data is going to stream in, like any other like file descriptor. It's kind of like you can think of this, by the way, as like a two-ended pipe with one end on one computer and one end on another computer. And it's just like you don't have to wait for you don't have to, when you're reading from a pipe, you don't have to wait for the other side to close.
Right. So
Mhm.
is it possible that the client gets the lines while the server's halfway done with?
Oh yeah, sure. Is it possible for the client to get line before the server has published it? Yeah, but it locks when it's reading in the data until it gets a whole line. So get line will do. That make sense? Yeah. Other questions? I saw another hand up. No? Yeah.
If there were 2 lines of output from the server, just get the first line.
In this case, if there were 2 lines of output from the server, it would just get the first line, yes. Yeah, they would do close. Same thing as before. When you get to the end of this function, it closes that socket, closes the file descriptor for you.
So the IO socket is like the actual way to run class query because the server.
Well, yeah, so the question is, hey, what's going on here? So here's the sock buffs sets up the buffered input output so that you don't have to deal with a while loop. It's doing the reading. Then the IO sock stream makes it into a C++ stream so you can use the little angle brackets, or you could use getLine or what have you. That's how that works. Yeah?
So, if you had your server running and it published 2 lines, and then
Yep.
you had called your client and it read the first line, and then you closed your server, and you called your client again, would it get the second line?
Yeah, good question. So the question is, if it did publish 2 lines and you ran this program twice, would you get both lines? No, because once you close that socket, you have to create a whole new socket. It's like closing a file and then trying to go and open the file again and read from it. It's not going to read the rest of the file for you. So it's not like it basically at that point, when your client stops listening, any data left in the stream is discarded by the operating system. It's basically what's going on. Yeah. Okay, so we've written a client. We could actually test it. I guess we
Sir,
say again.
we need client socket. Yes, sir.
Thank you. Thank you. All right, make time client. Okay, time client, and we don't have a server yet. Let's run the server. Time server. Let's do the concurrent one. Why not? Okay, and this is now myth53. So if we do time client myth53, and then 1, 2, 3, 4, 5, then it gives us the time. Okay. All right. That's the beginning of that. Okay. So let's dig a little deeper into some of the internet way of doing things. Okay. There is a command called wget. Wget is a command line utility that will do the following, like wget. Let's see, is this going to work if I do let's do it this way. We'll do it this way. web.stanford.edu/class/cs110, like that. Okay. It says that it did a bunch of stuff, and then it says, did it say how much data? Just says saving to CS110. If we look at, hang on. Yeah, vim CS110, there's our website. Okay, so wget allows you to get websites from the web, wget, allows you to do that. And it uses a particular protocol. Okay, it turns out this protocol is kind of interesting. If we were to do the following, so remember I used telnet before to telnet back and forth? You can actually telnet to, let's go to google.com. Actually, we'll do it, let's see. I think it's got to be www.google.com as it turns out. Google.com, okay? Okay, maybe not. Oh, I didn't put a port. Port 80. Hey, we're connected to Google. Okay, we're actually connected to Google, and Google's like, what do you want me to do? And it's just waiting for me to do this. I can type the following. Get, let's do slash, which would be the regular old main page of Google. Get slash. We have to do, let's see, get slash, and then, how do I do this? I think you do HTTP/1.0, like that. I believe that's the way the protocol works. And then, what do we have to do that? We have to say host. Host, and we have to say www.google.com. And if that works out, and I do one more new line, it brings up google.com. And there's your google.com. Okay, so if you know how to speak internet, you can actually request web pages just using a raw protocol for, in this case, the Telnet, which connects to the web server. The web server goes, what do you want me to do? You give it a couple commands, and then it pushes back the data for you. Okay, kind of neat, it turns out. We have to learn a little bit about that, about how that actually works. There's some other things that can happen in here. Let's say we do telnet, www.stanford, let's do, stanford.edu. And then let's say I want to do get/class/CS110, like that. This may or may not, well, we'll see if it works. HTTP/1.0. There's also HTTP 1.1 and there's 2.0. Once you get above, like, 2 and above, it's all encrypted, so this wouldn't actually work anymore. You'd have to like do a handshake with encryption and all that. So eventually, when we're teaching this class, that'll stop working because everybody will be encrypted, and then we'll have to figure something else out. But that's the way it goes. Host www.stanford.edu. In fact, I bet this tells us, hey, you got to go to the other page. Let's see, that, and what did I forget? Oh, I forgot that thing. Hang on. Yes, thank you. Forgot the port, so it never actually connected. There we go. Now we're connected to it. Get/class/CS110 HTTP/1.0, and then host www.stanford.edu, and there we go. Yeah. So in this case, it says, hey, we got a message back that said, hey, this moved permanently to HTTPS, which is the encrypted version. It doesn't want us getting the unencrypted version. Now you can actually fake it out, but in this case, it doesn't want us getting the unencrypted version, which is kind of nice. But that's the way that you get web pages from the internet. So let's write a little program to do this, to write that wget program. Yeah, question.
Why does it ask you to the host like twice? You know.
Yeah, you can. So it asks you for the host. Like you telnet to a particular website, and then it asks for the host. It may be that website has multiple hosts running on it that are all the same, different website addresses on the same computer. So that might be the issue in that case. I think that's the basic idea. So let's write wget. Okay, here's what we're going to do. We're going to take a look at a couple of functions. I'm not going to bother writing the one up here, but the first thing we need to know is we need to, like, if we have a URL, in other words, www.stanford.edu/some web page, okay, you need to basically parse it out. And this is the little function that does it. You can go look at that a little bit later, but it basically takes the address, finds the HTTP part of it, and then after that, the rest of it is or until the next slash is the actual, or until the last slash rather, is the actual address itself that you're trying to look for. So you're basically trying to get the URL, host, and then the path that it needs to get to. And that's the function that does that. Okay, let's look at a couple other functions. I'm actually going to write these ones. Webget.cc. Okay. Whoops, maybe not. Hang on. 110 fall. There we go. Networking. Webget.cc. Okay. So in here, let me make this a little bigger because there's a fair amount of code here. We are going to write some of these functions. In fact, let's write this pull content function first. Okay, here's what we're going to do. The pull content function needs to create a client socket, etc., because it's going to be the part of the program that is going to reach out to whatever website we want and say, hey, give me the data. Okay, so this is how this is going to work. Okay, and in this case, we're passing it in those components we got from the parsing. Okay, so we'll do something like this. Int client equals, this should start to look relatively familiar. Create client socket, and then components dot, it's a pair, so there's a first and a second. Components dot pair first, and then let's see, let's do the port in this case. The port is going to be K default HTTP port because it's going to be 80 as it turns out. HTTP port like that. Okay, and then if the let's not worry about the error right now. Well, I guess we can. Might as well. If client equals K client socket error, you can do, of course, you can do error correction or error checking on this. If it equals that, we can say C error could not connect to the host, something like that. Okay, and then end L, like that. Okay, and then and then let's return actually. If we have a problem there, and then otherwise we're going to actually set up the sock buffer again. Sock buff SB, and in this case it's going to be the client, and then we're going to do an IO sock stream. And it's going to be SS ampersand SB like that. And then we're going to, now we have to actually issue the request. At this point, it's not just as easy as the time server, where before we just said, just give me whatever you got. Now we have to talk internet. We have to talk this GET protocol. Okay, so let's call a couple functions which we'll write in a second. Issue request. Okay, we're going to issue the request, pass in the file descriptor, and then pass in components.first and components, I don't know why we didn't do it with a pair, but we didn't, components.second. Okay. Then we are going to skip what are called headers. Headers are extra information that your website gets based on things like, let's see, some of the headers are, hey, I'm sending this encrypted, or I'm sending this compressed, or I'm sending this in some other form. And we want to just skip those, as it turns out, because we're just getting the website. We don't care what the headers are for our particular version of this. If you were writing a real version, you probably would. But let's do skip header. Okay, and then we're going to save the payload. Once we get it, we're going to save it. And I'm not going to write that function, but file name, and then components.second. And we'll write the get file name as well. Okay, so that's what we're going to do in this pull content. We're going to set up a socket. We're going to try to connect to it, and maybe we can write connect properly. Okay, we're going to try to connect to it. Then we're going to set up a little file descriptor and a stream to be able to read from it. Or we've got a file descriptor. We're going to be able to read from it using nice C++ ways, and that's what we're going to do. Okay. All right. So let's go and look at the issue request, because that's the part where we're going to have to send that get command that we just learned about, that we just saw with Telnet. Okay. It's actually fairly straightforward. SS. Right? We are going to send get with a space, and then we're going to send the path that we got passed in, and then we're going to send http/1.0. Then we're going to send \r/n. Who's seen \r before? Yeah, do you know what it means? It means carriage return, which means go back to the beginning of the line, but don't go to the new line. The new line does the new line. In Unix, \n does both. In internet world, you need to send both a carriage return and a new line. This goes back to older days where they had two characters to do that. But that's the way it goes. So you have to do that. But that's the first line. Okay, and then semicolon. And then the next thing that we're going to do is we're going to send SS, and then we're going to send host. And then that's going to be the host that we got passed in. Okay, and then we're going to send that in there. End L just won't do it on its own because you have to have these so that the web server will actually read it correctly. Okay, and then we send a blank line like that. Okay, and then finally the last thing we do, and this is kind of important, we actually have to flush the buffer. it turns out that without flushing the buffer, the network, the socket might not actually send the data, and you'll sit here and block all day. So you have to actually remember to do that, and some people forget that, and it's kind of annoying when you do that. But that's it. Now we've sent the command. Okay, that's the request. Okay, once we question back there? Yeah.
Yeah, why do we have to do the /r again?
So yeah, why do we have to do the \r? \n in Unix speak takes the cursor, goes back to the beginning of the line, and then goes to the next line. In the rest of the world, in basically the way networks work, new line just goes to the next line, but doesn't go to the back. It doesn't go to the beginning. It goes straight down. It doesn't go back to the beginning of the line. That's the way it works. So, so you need both a carriage return going back to the beginning and then a new line going to the next line. Why? Because networks are old. That's kind of the reason there. Yeah, and they all have to talk exactly the same. So it's not like we can go change it and say, oh, we don't want to send that anymore. Yeah, good question. Okay. So let's look at the skip header. The skip header is actually really a simple program, or a simple line. The skip header basically says string line. And remember, what we're doing is we're reading a bunch of things that we don't care about until we get to the actual payload. Things like, hey, I'm sending this in some format or whatever. Okay, so we're just going to do this, and we're going to do the following. We're going to do loop, of all things, get line, and then ss line. Okay, and then while, did I do something wrong here? No. While not line dot empty, it's a string thing, while not line empty, and line is not equal to \r. It turns out, and this is just a weird anomaly, some websites won't give you that won't give you the \r, just gives you a new line. So if there happens to be a \r on its own, we have to also just know that that's the end of the line. Not really that important. Just know that we're skipping a whole bunch of a whole bunch of lines until we get to a blank line. After that first blank line, the rest is what we're looking for. Okay, so the rest is what we're looking for here. I guess we have to write the get file name one as well. The get file name here is going to do what? It's going to basically check the path and do the following. Path, if the path is empty, if I just ask for google.com, what's the file name going to be? Any ideas? Index.html, that's what we're going to use. It's kind of the default web page. You've probably seen that one before. It's the default. So basically, if you have an empty string or path size, -1 is backslash, okay? It means that we're not going to actually have a file name to look for, so we're going to return index.html. In other words, we're going to say, if you just give me a path with no file name at the end, just call it index.html. That's all that's doing, okay? Otherwise, we're going to actually have to look for the file name. Size t found equals path.rfind, which is reverse find. It finds the last slash in here, and then return path.substring substring found +1. In other words, return the actual path. Okay, so that's that. All right, and then I'm not going to write the last one, but it should be in here somewhere. Where did it go? Looking for the, hang on, I think it's at the top. We are looking for the, where did it go? Oh, hang on, which one did we not write? Did I miss one here? Save. There it is, save. So save payload goes and actually gets the data from it. Save payload goes, gets the output file name, or opens the output file name, reads all the data in, and then writes it out to the file. Okay, that's all that's doing. Okay, all right, did anyone see any typos in there? Make web get. Make web get. Oh, there was a couple in there. Found is not declared. Hang on. Let's see. Oh, found is not declared. Looks declared to me. Oh, up here. Nope. Same thing. I'm not sure. In the interest of time, ready for this? Webget original. Webget. All right, that one should do it. Make webget, because that's not the important part. Okay, hold on. There we go. We'll go find. That's the way you find bugs if you already have it written. So for what it's worth, and then webget. Now, what are we going to do? We're going to do like web.stanford.edu, and then let's see, slash. Let's do CS1 or class slash CS110 slash. I believe that should work. There we go. Total number of bytes fetched 16,292 less index, and it should have called it index.html. There's your CS110 website. Okay, so that's how that works. Now, that was a lot of code that we just wrote. What questions do you have about this stuff so far? Yes? Good question. Did we parse through any of the HTML? No, we just got the entire site and just dumped it to the disk. So it's actually an HTML file still. Yeah, or whatever it happens to be giving you. It just dumps it straight. That's what wget just drags the entire file in, and you deal with it after that. No web processing at all, or no HTML processing. Yeah.
And can we navigate the website?
Can you navigate the website? Well, not with wget, but you could read So how's a web browser work? Like this leads into like how does a web browser work, right? It gets the web page, and then it looks through it, and then has all the links in there. And then it puts a little GUI up there for you to think, and it makes the links blue. When you click on a link, it gets that web page. And you click on a link, and it gets that web page, and so forth. It's just doing basically this. It's getting the HTML. By the way, it's also getting all your JavaScript and all your CSS, which formats the page, and it gets and it does that. And so, but once it has the page, it renders it, and then is just getting the next web page, getting the next web page, getting it. Now, turns out HTML files can load other things, like it can run JavaScript, which can then load other parts of the website and so forth. And so so there's lots of, when you do your browser and when you're going to write a proxy server, which you're going to see how many different files get downloaded when you go to a particular website. It's lots of them in many cases. Yeah. Question. Are these operations thread safe? In this case, yes. I mean, once you accept the client, anything you do with that file descriptor is thread safe. And that's really all we're doing here, is we're just dealing with a file descriptor and reading from it and writing to it. That's really all it is. It is a two-way file descriptor, by the way. You can read to it and write to it. The socket stream allows you to write and read, which is kind of nice. Yeah?
The index.html looked like it came in formatted. Is that like, or was it not formatted, but it's like randomly sourced?
It looked like it was formatted? Well, it came in, I mean, like when I wrote this, when I put the website together, I made it look like this. I mean, I put all the tabs or all the spaces in there.
It reads in the tabs.
It reads in the entire file. Whatever the file is, it reads it in. It could be a PDF, it could be a binary, it could be whatever you want. But whatever it does, it reads the whole thing and then drops it on your disk. Okay. All right. So let's see. That one was creating the socket. We did that. wget. We know. Any questions about the actual protocol now? Does it seem strange that you've got this protocol that like every time your browser goes and requests a web page, it actually sends get to like literally send GET and then like the thing out there? Somebody made this up a while ago. I mean, they could have done it in a binary way. Now, as I said before, actually HTTP/2.0 is a binary format. It's not just text anymore. It's a binary format. So that's another reason you can't use it as a demonstration in class, because it's just binary data. It doesn't look as nice.
How is it that some browsers would claim to be faster than others? Is it all just pre-caching?
How is it that some browsers would claim to be faster than others? You mean in terms of like, well, I mean the program is really the bottleneck. It's not really well, I should say that. The pulling the web pages is definitely going to be the bottleneck, but rendering them might take less time in some browsers and so forth. It's not about there's nothing that the browser can do to like speed up the network part of it. That's not going to be able to do anything. Other questions on this? No? get is kind of cool. You can also do, I believe it's put, and you can also do post, which actually sends data back to the server. So you can post data there. If you've done any web design, you'll know that you post data back to your server, and it allows you to run programs and so forth on the server. Okay. As far as let's see, skip header was concerned, the headers are just all the junk that comes before the thing. In fact, I don't know if there are any headers associated with. Let's do telnet to web.stanford.edu 80, and then we will do get /class/cs110/ http/1.0 host web.stanford.edu. Before I hit the next return, I'll clear the screen, and there we go. Let's see if there's any headers that came in here. Yeah, so here's all the header stuff that came in. All of this is header, and we ignore all that. And notice there's a blank line after it. Those are the kinds of things that the header, in this case, the headers say, hey, what kind of server is serving this? You might care about that. What kind of accept ranges is like, what kind of data is it? In this case, bytes. Connection, it's going to close the connection after it gives this to you, and then it tells you that it's HTML format. So that's what the headers are. Yeah.
So when you're like sending a request, would you just include the header and like, can you like have can you have a header in the request?
Can you have a header in the request? Yes. In fact, the way we did, remember that blank line we sent at the end after we do the host? You could send other headers in there. And one of the headers might be, hey, I can accept zipped files, so if you want to compress it, now I know how to uncompress it. Or it could say, hey, I'm expecting a certain type, or and so forth. So yeah, your browser sends lots of headers. And in fact, when you write this, proxy server in a couple weeks, you'll have to send a couple headers here and there. And obviously it's in the assignment itself. Okay, good questions. Let's see, that was the skip header. Let's see, the get file, the save payload. We didn't really go over that too much, but basically that reads the details of the file and then saves it to disk. Okay, that's your introduction to networking. Next time we will go through a little more detail of some of the lower level stuff, like what's happening behind the scenes with this get client socket and so forth. Okay, there's some lower level function system calls that are getting called to set things up. All right, see you in lab.